Hi, my name is Natalia. Today I'll be talking about Bayesian hypernetworks. So the background on this is that it is based on Bayes' rule. So Bayes' rule is important because it is a mathematical theorem that is about how to update beliefs as you encounter new evidence. And so a hypernetwork is a probability neural network. It outputs parameters on a deep neural network. So it is structured so that the hypernetwork and the primary network work together to form a single model, and this whole thing is trained by backpropagation. Usually you can use it on like a convolutional neural network, and you just add statistics to each neuron so that you're able to see how well your inputs from your testing data will fit onto your training data. So DNNs show a single most likely value of parameters usually, so it'll tell you how sure it is between classes, but it'll never tell you uncertainty. So hypernetworks are really great because they correlate between the parameters and it shows a better confidence estimate. So this is really great for model uncertainty. They tested against regularization, active learning, and anomaly detection, which I'll talk about later. So it works because Bayesian hypernetworks take random noise as a distribution, and from here they output a sample from the approximate posterior for the primary network of interest. It basically transforms simple noise distribution into a probability distribution over the parameters of your primary network. This paper uses an invertible hypernetwork. It enables Monte Carlo estimation of the entropy term in the variational inference training objective. Now, variational inference is the most popular approach for Bayesian deep neural networks right now, and so that's why they use that, and they were able to use Monte Carlo sampling, which makes it very easy to furnish the decision maker with a range of possible outcomes for any choice of action, and it makes it really easy to compute, so that's why they also use the invertible hypernet. Now, DGNN is a generative model of the network parameters which transforms a simple noise into a samples from a distribution. So this is where our distribution is coming from, and we're training it using inverse autoregressive flows. I'll talk about that soon. And from this distribution, we're going to learn our approximate posterior distribution, which is the conditional probability assigned after the relevant evidence is taken into account. And of course, we're using variational inference, which is our most popular approach today. And training these models is going to be using the change of variables formula. You're going to be computing the log determinant of the inverse Jacobian of the primary network. Real MVP is really great. Architecture that they use is unsupervised learning algorithm, and it's good for nonlinear spaces. So you compute the exact log likelihood, and they're good for exact sampling and exact inference of latent variables, and it gives you a really good interpretable latent space. So it's really just it's a nice algorithm for computing nonlinear models, and it doesn't rely on mean squared error, which is interesting. And so this generates sharper samples as a result. And so the second architecture that they compared it against was inverse autoregressive flows, which consists of a chain of invertible transformations. And I put a photo of that right here. Each transformation is based on an autoregressive neural network, and it's really good for high-dimensional latent spaces. They decided that IAF was really best for the application at hand. Also, it's important to know that it's very quick at sampling, even though it'll take a little longer to train. Okay, so on top of these architectures, they use MADE, which is an autoencoder neural network. So you want to use an autoencoder neural network because you can teach it through backpropagation to reconstruct its output layered instances of a particular class. So you don't need to train it on instances of any other class. And then when you want to classify new instances, you feed into the autoencoder at the input layer, obtain a reconstruction of the output layer, and compute the reconstruction error. And the reconstruction error is a measure of the distance between the reconstruction and the input. But if the autoencoder generalizes well to a new instance and reconstructs it properly, then you'll have the same class of the instance. Basically, it's really good for determining it's really good for our purpose. So we're using autoencoders, and we're also going to use ATOM, which is an algorithm for gradient-based optimization of stochastic objective functions. So stochastic objective functions. So stochastic optimization refers to the collection of methods for minimizing or maximizing the objective function when randomness is present. So it's just going to be really good for optimizing. And you're also using ReLU layers, and which is of course, if it's negative, then you have 0. If it's positive, then you have a linear. You're going to be using gradient clipping, which is really for managing the size of the weights. And then also we're going to be using 128 mini batch size. Okay, now we're going to be, the base of this paper is based on variational inference. So equations 1 and 2 show us variational inference. The equation 2 is our evidence of the lower bound. We want to minimize this on the marginal log likelihood of the data under the statistical model. And then we can approximate the posterior distribution under unobserved random variables. So now we're going to decompose these to make it work for us. Equation 3 is us decomposing the log into stochastic gradient methods for optimization. And then equation 5 holds Q of theta, and this variable shows us, it's actually very important, it's for the learned approximation to the true posterior. And so we want to be able to use this. So equation 6 shows how we decompose this using an invertible H and changing that variable. Equation 7 is just something that they use to normalize their weights, or weight normalization parameterizations. They tested these experiments on MNIST, which is our numbers image database, CIFAR10, which is our image database, and 1D regression. And they found that the best Bayesian hypernetwork is made with inverse autoregressive flows. Keep going on that. So let me show you real quick an illustration of Bayesian hypernetworks. The first one is non-Bayesian deep neural network. So you see here, there's a key thing you need to pay attention to is, that blue color and the red crosses. So the red crosses are the examples from the training data set. And the shaded region, the blue part, is half standard deviation in the posterior on the predicted mean. So basically, you can see here that the traditional Bayesian hypernetwork kind of misses some of the examples. They don't fit the model. But HyperNet is what they only used it on, a small part of the network. They only used statistics on part of it. And you see a much larger shaded region. And a full hypernetwork, you can see all the crosses are inside of the shaded region. So you're able to really tell what will fit the model correctly. So they did anomaly detection on MNSIT. Here is a box plot of the performance. So Bayesian hypernetworks using inverse autoregressive flow had the best accuracy at around 96%. You can see that they also applied dropout, and Bayesian hypernetworks using real MVP, and the accuracy was not as high. Also, inverse autoregressive flows are really great here because you really don't need to be using such a computationally heavy real MVP, because you really only want to approximate the likelihood of the generated samples and not the arbitrary points, which real MVP kind of really goes very much in depth. Whatever. So figure 5, it also shows the results on adversary detection. They changed it on these with IAF, RNV, real MVP, and dropout again. And so what you're looking here for is for the accuracy to be high throughout. So you can see that some Bayesian hypernetworks with inverse autoregressive flow had the highest accuracy, meaning that at the end of the sample, you can see an increase, and it's constantly higher than the other architectures. So higher accuracy overall. So here we're going to be using Monte Carlo estimation to estimate the predicted posterior and use this to score data points on MNIST, which again is your numbers data set. And so they found from previous finding that these acquisition functions were really good for scoring anomaly, and their maximum confidence of the softmax probabilities really gave the best performance. So what they did again is they excluded one class in the training set at one time. Again, remember when I talked about autoencoders. So you're taking the excluded class out of the data set as out of distribution samples, and you're using that to compute. Okay, great. So Bayesian hypernetworks are great because they allow you to have the network tell you when it's wrong or when it's unsure of something. And this can be scaled to real world tasks such as anomaly detection on all fronts. And of course, there's other things too, but I only really care about anomaly detection. Also, I learned that you can use variational inference for Bayesian hypernetworks, and you want to use an autoencoder, and you also want to use things for optimization. So use stochastic optimization so that you wouldn't be stuck in front of a computer for the next year.